Hello and welcome. Now in this video we'll try to learn the expression for work done to rotate an electric dipole in a uniform electric field. As we have already studied about the torque experienced by an electric dipole in a uniform electric field, so if we want to rotate an electric dipole in a uniform electric field, a work is to be done against that torque. So suppose we have an electric field E, and in the electric field we want to rotate a dipole by an angle of d theta. So this is QE, this is QE, and we want to rotate this dipole by an angle d theta, and we have to find the expression for work done while rotating this electric dipole. As we know, the torque experienced by this is given by PE sine theta. So this tau is a variable torque depending upon the value of theta. So if you want to know the work done, we have to use the formula for the work done by a variable torque. So work done by a variable torque is given by W is tau d theta from initial value theta 1 to theta 2. So if you want to rotate the dipole from initial angle theta 1 to a final angle of theta 2, we have to use this expression to calculate the work done. So now substituting the value of tau, this W is given as PE sine theta d theta from initial value of theta 1 to final value of theta 2. So PE integration of sine theta d theta from initial value of theta 1 to theta 2. So this is PE. The integration of sine theta is minus cos theta from theta 1 to theta 2. So we can write minus PE cos theta from theta 1 to theta 2, or it is minus PE cos theta 2 minus cos theta 1. Or if we adjust this minus sign to the bracket, we can write PE into cos theta 1 minus cos theta 2 is the expression for work done. So this is the final expression for work done if you want to rotate a dipole in an electric field from initial angle theta 1 to a final angle theta 2. Now some special cases. Special cases. Number 1. When theta 1 is 0 degree and theta 2 is theta, then work done is PE cos 0 degree minus cos theta, and the value of cos 0 is 1, so PE 1 minus cos theta. So if the dipole is held along the axis of along the direction of electric field and if you want to rotate it by an angle of theta, the expression is given by W is equal to PE1 minus cos theta. And case number 2. Case 2. When theta 1 is 90 degree and theta 2 is theta. So, if the dipole is initially held making an angle 90 degree with the direction of electric field, and if you want to rotate it to an angle theta, then the expression for work done is PE cos 90 degree minus cos theta, and this is PE, as the value of cos 90 is 0, so this is minus cos theta, or we can write it as minus PE cos theta, or this is minus P dot E. So this expression is called potential energy of an electric dipole. So if you get a question in the board that find the expression for potential energy of an electric dipole in an electric field, then we have to derive this one first, that is work done PE cos theta 1 minus cos theta 2. Then we have to apply the special case from theta 1 equal to 90 degree to theta 2 is equal to theta, and we get the expression for potential energy of the dipole. And a very important question related to this potential energy for board exam is the stability of electric dipole. Electric dipole in a uniform electric field. And usually a question in the board is asked that for which orientation of electric dipole it is in the stable equilibrium. So question is, for which orientation of electric dipole it is in the stable equilibrium. And we can give the answer that for stable equilibrium, the answer is for stable equilibrium potential energy of dipole should be minimum, because we know that when potential energy is the minimum, the stability is maximum. So for stable equilibrium, the potential energy of the dipole in the electric field should be minimum. So if we consider three specific cases, first the expression for potential energy is minus PE cos theta. So if theta is 0 degree, if theta is 0 degree, potential energy is minus PE cos 0, that is 1. And if theta is 90 degree, PE is minus PE cos 90. The value of cos 90 is 0. So the PE is 0. And the third one is, if theta is 180 degree, potential energy is equal to minus PE cos 180 degree, that is minus 1, that gives potential energy is equal to PE. Now see, in this expression, the potential energy is minus PE. In this, the potential energy is 0, and in this, potential energy is PE. Can you tell which angle has the minimum value of potential energy? I think it is very clear that when angle theta is 0, the potential energy is minus PE, which is even less than 0. So out of these three standard values of angle, we can see for angle 0 degree, the potential energy is minimum, that is minus PE. So the electric dipole will be in stable equilibrium when the angle theta is 0 degree. So out of these three, we can say the electric dipole will be in stable equilibrium when theta is 0 degree. That is when dipole is along the electric field E. So this is the expression for work done and the expression for potential energy and the special case when this dipole is in stable equilibrium. So thank you very much.